it make sense?
Kind of.
Okay, so basically we can define a plane with a position vector and two direction vectors. And provided that the two direction vectors are not collinear, that's all you need to define a plane. Now, the second way of looking at it is all you really need to define a plane is three non-collinear points. If you have just 2 points, the best you can do is define a line.
Mm-hmm.
But if you've got 3 non-collinear points, now you're able to position your plane in 3 space. When we get looking at the vector definitions, if you've got 3 points, then you've got enough to make a position vector and 2 direction vectors for that plane.
Okay.
And when you multiply those direction vectors by scalars s and t, you can actually get to any position that you might want to on that plane. So I don't know, there were little manipulatives on there where you could stretch the vectors out, and you can see eventually that you can trace out any position on a plane as long as you've got those 3 independent points, and you can turn them into vectors. Does that make sense?
Yeah.
All right. So we had an issue arose where we had this set of points. So the original vector equation was 2, 3, 1, which was our position vector, and then s times 3, 0, 0, and t times this last -1, -2, and 1. And so in the preamble, we had this vector definition for a plane, and it just turns into that parametric definition for the plane. And I put up this new question: does the point 7, 1, 2 lie on this plane? So how can we go about solving this? Tackle it. Any ideas? Lindsay knows, but she's not saying. So 7, 1, and 2, we're going to have to get consistent values for s and t over here. And so we can actually make some equations. 7 is equal to 2 plus 3s minus t. So there's one equation and 2 unknowns. And y is equal to 3 minus 2t. But our y coordinate is 1, so we can actually substitute a 1 in there. And z is equal to 1 plus 1t. Z is equal to 2. And so z is equal to...
Jersey, can I come to the office, please?
All right. Now, the way the equation of this plane was set up, we had this super convenient second vector with all these zeros. And so we can actually just pull a t value from either equation 2 or equation 3. If we didn't have that, we'd have 3 equations and 2 unknowns, and we'd use 2 of them, figure out our s and t values, figure out if it was consistent with the third one. But at this point, actually, we can just find a t value from equation 3. So by equation 3, my t value is equal to 1. And so I'm going to sub into equation 2. And I'm going to see that 1 is equal to 3 minus 2 times 1. So far that's fine. And as you can see, basically you can have any value for s here at all. And so it's going to be consistent. So this one's actually pretty easy. We can figure out our t value, and it's not going to cause any problems with any of the other equations that we have. So sub it in, it works. And if I put my next value in, t is equal to 2 plus 3s minus 1. So 7 equals 2 plus 3s minus 1. So that's 6 equals 3s. S is equal to 2. T is equal to 1. Everything's consistent. 7, 1, 2 does lie on the plane. It's just a matter of picking the right S value. Okay, so there's a does it lie on the plane question.
All right.
That's the easy version. In the more complicated version, you'll have to use elimination to figure it out,
Okay. Yeah.
or possibly substitution. Okay, I have a question for you. So give the equation of a plane that contains the line
Callie Hayes and Tori Finger, come to the office, please.
So a line that's defined by the position vector 1, negative 2, and 1, plus the direction vector. I've got 3, 2, and negative 2, but it doesn't really matter. Okay, so there we are. We want to come up with the equation of a plane that contains this line, and this is the vector definition of that line.
Aren't there infinite sort of planes for a line?
Totally, yes. So in other words, this is one of those things where, there is no single correct answer. There are lots and lots of planes that are going to contain that line, an infinite number. I just want one.
Yep. So could you just, I don't know, plug in a second direction vector? Or I don't know.
Perfect. That is the answer I was hoping for.
Good.
Yes, so far this, there's the line. Let's just plug in a second direction vector, and it's going to turn into a plane, just like that.
Doesn't really matter.
Doesn't matter at all, actually, yeah. So 1, 1, 1. There we go. So yeah, there we go. We've actually got a plane now that contains this line. And you're absolutely right. There are an infinite number of them. You could pick anything that's non-zero, and that's going to do the trick.
Okay.
Good so far?
I think so, yeah.
Yeah. So once again, all you need is, a position vector, 2 direction vectors, and you can get a position vector and 2 direction vectors out of 3 points. Okay, so here's a tricky one. This one's right out of the CEMC questions. So we have 2 lines that are parallel, and the first one's defined by 1, 0, negative 2 as a position vector, plus s times 2, negative 4, 4. And then we have a second one that's parallel to this first one. Negative 2, 3, 0 for a position vector. And then t is equal to negative 1, 2, and negative 2. Okay, so those are parallel lines. Now, out of interest, we should stop here and talk about how could you tell that those lines are parallel by looking at, Lindsay's pointing. Either she knows how they're parallel, oh, she does, or I've done something wrong. She knows how they're parallel. Okay, how could you tell that those are parallel?
The direction vectors are scalar multiples of each other.
Yeah, right on. Yes. They're scalar multiples. This is
Yes.
-2 times this direction vector. So I take that direction vector, multiply it by -2, I get that direction vector. These are two parallel lines based on their direction vector. So here's the problem. I want to find the equation of the plane that contains both of these parallel lines. But the second problem here is I don't have a direction vector that's going to define a plane. I've just got two direction vectors that are going in the same direction. They're parallel. So how am I going to get another direction vector so that the plane contains these two lines? I'm just going to stand here drawing this. So there we go. There are my 2 points. Here go my 2 parallel lines. If I could just find any vector that's not parallel to these 2 direction vectors that's on that plane, I'd be away. Any ideas yet?
Do we do something with the two? We're going to do stuff with the 2 direction vectors. Do we cross them or?
Oh, I like that idea.
You
You know what? That's a good idea. The thing is, if we did the cross product, we wouldn't get an answer because they're parallel. So when we did the cross product,
Right.
we'd actually get like 0 for an answer.
Right.
But I have to say, I really like that idea. That's a great idea. Other than, it wouldn't work.
Yeah. I'm just thinking of
It does show you're thinking correctly. That's good.
good to hear.
Okay, you ready? Here comes the answer. Or a possible answer. All we have to do is pick a point on this line and a point on that line, and then we're going to have a second direction vector that isn't parallel with either of these two, that isn't a scalar multiple, and the handy ones are right here. So those position vectors will do. We could pick any 2 points that are on those lines, though. Okay, so let's find a second direction vector, and we're just going to take 1, 0, and -2, and we're going to subtract -2, 3, and 0. And as long as I get this right, 3, and 0 minus 3 is -3, and -2 minus 0 is -2. So there's my second direction vector. And so I'm just going to use this for my position vector. So I'm going to start there, -2, 3, 0 plus s times, and I can choose either of these direction vectors. And then I'm going to choose our freshly developed direction vector. And so now I've got it. I've got the equation of a plane that's going to contain those 2 lines, and it's going to be a plane because I've got a direction vector that's not parallel.
Do we need a T in front of the there?
Yes, I was going to go with the version without the T, but yeah, we could have a T, I guess.
Okay, good.
Good choice. All right, let's see. That's pretty much it. Oh, they've got they have another good example here. Okay, so here's the question. plane is going to contain oh, you're going to get this in a second. So it's going to contain this line. Maybe this isn't such a hard question after all. 3, 5, -1 plus s times 1, 1, 2. So it's got to contain that line, and it has to be parallel to a second line I'm going to put a T in front of this one just to satisfy the audience. Okay, so it has to contain this line, and it has to be parallel to this line, and it has to be a plane. So we like need, you know, we need another direction vector. You can get this. I know you can.
I'm getting there. I'm getting there. So we need the first line has to be on the plane.
Yeah.
Second line has to be parallel to the plane. So is there what do we just do? Is it different to that? Like
Yeah.
it's the same thing? Pretty much?
It's almost the same thing.
Almost.
This contains the line.
Yeah.
Or sorry, this line is contained in the plane, and the plane is parallel to this one. So this line is like up above the plane and never intersects it. Okay? So we have a position vector, we have a direction vector, but to get the plane, we need another direction vector. And let the record indicate that Lindsay is pointing to this direction vector right there. So we're just going to make it 3, 5, -1 plus s times 1, 1, 2.
Oh.
And then the second direction vector that we're going to use, it skates us all around the plane. -2, 1, 8. Okay, so it contains that plane for sure. And it's got the same direction vector, and so it's parallel to the second line. So it's really just kind of an extension to that question about find a plane that contains this line. All right. Hey, I think that's pretty good.
So since it's parallel to the other one, that's why we have to pick that direction vector?
That's right.
That's
Yeah.
Okay.
So if it's parallel to that,
Gotcha.
then it's got that direction vector. So the direction vector for this is parallel to that direction vector.
It's pretty good.
All right. That's it. So I guess I hadn't realized it when I made the schedule, but we kind of had 2 tests 1 week apart in the original schedule.
Yeah.
I get the impression that people want to skip that test. So we'll just have a 2-week test at the end of the course. So that finishes it up. The last lesson is next Friday, 1 week from today.
Alrighty.
All right.
So is it just going to be a little bit of a bigger test then?
Yes. So it'll just be about this. It'll just be like 5 or 6 questions. It'll be about the same size.
Okay.
Yeah.
Just including both sorts of stuff.
It's just going to include both units. Yeah. But it'll just be a 2-week. It'll cover 2 weeks of stuff. I guess.
Yes.
Yeah. I guess it's going to be 11 lessons altogether. So yeah, that's about 2 weeks.
Okay.
Yeah. All right.
Sounds good.
So I'll put up the homework and
Yep.
We'll meet up on Monday.
Alrighty, that sounds good.
Okay. See you, Jeff.
All right, see you later.